The framework of this video shows the implementation of a sophisticated artificial intelligence autonomous vehicle platform. Here I use advanced computer vision methodology to distinguish different objects, colors, and natural surroundings of the environment, and can apply liquid mixture using onboard sensors. The system architecture consists of a top layer hardware, a middle layer hardware, and a lower layer hardware. That is layer 1, layer 2, and layer 3. It also includes radio telemetry and radio control system and power management. So layer 3, that is the lower layer of the architecture, includes motors and the motor drivers. This layer is responsible for the propulsion and the steering of the robot, in this case the artificial intelligence vehicle system. The second layer, that is the middle hardware layer, provides the system with its autonomous movement and path planning capabilities. In order to provide communication, redundancy, and remote control, the system was equipped with several communication systems which are under the control of the autopilot system. Some of these systems, like the GPS, are part of the second layer, that is the middle layer hardware, and are directly used by the autopilot subsystem. The telemetry system and the remote control receiver are communicating with the autopilot board using different interfaces. The top layer of the architecture includes the microcomputer and an optical camera, which are needed for the computer vision tasks. The propulsion system of the autonomous vehicle is implemented using two brush DC motors with integrated encoders. They have metal gearboxes and are intended for operation at a nominal voltage of 12 volts. The motors have gear ratio of 19:1, which provides 500 RPM without a load. For turning left and right, I use the smart steering servo motor, which is extremely suitable in order to perform object detection. I use deep neural classification models. Their convolutional layers are the key component which enables image processing and object detection. These are filters which extract features from the previous layers in order to transform the input data in a form that is more useful for representation. the workflow for the training of the system to recognize the environment. In this part of the application, I use the TensorFlow Object Detection API, which I used as a training platform. The workflow contains 4 main stages: preparation of the environment, preparation of the data sheets and data sets, training, and then implementation of the object detection model. The input data set is required to contain images that have objects of interest related to this application. In order to train a good detection model, TensorFlow requires hundreds of thousands of images. However, instead of training a model from scratch, it's possible to retrain a pre-trained neural network model and then use smaller amounts of images. The visual odometry is a technique for autonomous navigation, motion tracking, and obstacle detection and avoidance. It also allows the robotic vehicle to localize itself by using only a stream of images captured by the camera, which is attached to the outside system. Several small form factor computer boards were used in the implementation of this autonomous vehicle. A small Raspberry microcomputer, which is the core of the top-level hardware layer of the smart vehicle platform, supports several cameras, including the commercially available cameras and other advanced real-sense depth and tracking video camera systems. These systems are used in order to detect different colors and also develop a custom Python script that allows the detection of specific predefined colors. I also used OpenCV to run the programming scripts. The computer vision algorithm is set to recognize different colors, such as red and green. During the mission, the computer vision algorithm is running constantly on the artificial intelligence vehicle controlling system. An additional benefit of the visual navigation system is the fact that the smart vehicle can track rows of objects in the field completely autonomously. And also by using the capability, the robotic intelligent vehicle can create a map of the area and save it for future missions. as the visual navigation solution is not based on GPS location data, the intelligent vehicle creates its own relative coordinate system and stores its initial position. The artificial intelligence vehicle controller system. The DC motors are connected to the driver board. The drivers are installed in a mirror configuration, so it is required to reverse the polarity of the power supply to one of the motors because of the reasoning that the motors are DC. The change of polarity will reverse the direction of rotation of the motor shaft and will synchronize the direction of the rotation of both motors. The main neuromorphic architecture and CPU autopilot controls the motor driver via the pulse width modulation signals, that is, the PWM signals. These signals have different levels in order to determine the direction and movement. A high-level signal will drive the artificial intelligence vehicle system forward, while a low-level signal will drive the artificial intelligence robotic vehicle backwards. The main controller controls all the hardware components of the middle layer, that is layer 2, which are above the DC motors, the motor driver shield, and the servo controller. Also, the primary GPS and compass are required to provide the autopilot with positioning data during movement, while the secondary GPS system is an optional component and is normally used to improve localization precision. The autonomous vehicle presented in this video relies on computer vision technologies and image processing algorithms for the automatic detection, such as colors and whatever it is in its surrounding environment, as well as for visual navigation and the avoidance of obstacles. Supervised machine learning approaches. A training model was used. The faster CNN convolutional neural network is canonical model for deep learning object detection. The time it takes to train the model depends on the number of images, their resolution, and the hardware parameters of the unit in computation. After the training, the last step in the process is to export the trained model and use it in its actual practice as a demo model. In certain situations, the autonomous vehicle has to implement autonomous tasks that are extremely complex. To do this, the vehicle can be configured
to navigate on its own and without any predefined routes, but again, without damaging anything and any on its path. So the goal of the smart vehicle is to construct a map of the unknown environment and to localize itself in it. In the computer sciences, normally this is a problem. It's known as the simultaneous localization and mapping, otherwise known as SLAM, S-L-A-M, SLAM problem. The most recent scientific solutions to solve the SLAM problem are based on visual methods for positioning, also known as visual odometry. This approach allows the estimation of the location of the robot based on 3D motion of the camera in space. There are two main ways to implement visual odometry solution: by a single camera or by the use of two cameras. The use of two cameras calculates the depth by estimating the disparities between the matching key points in the images from both cameras. The visual odometry is a technique for autonomous navigation, motion tracking, and obstacle detection. For this demo, the Mission Planner software is used to make the vehicle navigation autonomous. This application allows the user to predefine a specific route so that the vehicle will follow using the GPS navigation system.